Let's learn about weight. What is it? Where does it come from? Why does it happen? What's the deal with it? Weight. Okay, I'm really tempted to start singing the weight, but I'm not gonna. So weight. What is weight? Okay, so the first thing we know is that one property of matter is that matter has mass. Matter has mass. Okay? And that mass, we know, is measured in kilograms. Mass is measured in kilograms. Okay? If mass is measured in kilograms, how is weight measured? Now, someone's going to say pounds. I'm going to give you this face. Nothing is measured in pounds. Okay? From our perspective, besides the money, pounds do not exist. Okay, mass is measured in kilograms. So we need to make a distinction between mass and weight. Okay? So mass is like a, if you want, property of the matter. Okay? It is basically a measure of how much matter there is. And it sounds a little weird, but basically, there's kind of a couple of ways of sorting this out. And I think we talked about it a little bit yesterday. If we take some mass, we take it out into space, and we start to try to push on it or pull on it, we'll notice that it will like start to accelerate, right? Okay. So let's say we apply like a set force on it. Let's say we apply a 100 Newton force, on this mass. We just start pushing it. I don't care how we're pushing, we just start pushing it. It will start to accelerate, right? Now let's say that we double the amount of mass here, right? What if we push it with the same force? What can we expect to happen with the acceleration? We've got double the mass but the same force. What kind of acceleration should we have? A lower, and in fact we'll have half the acceleration. If we triple the mass, we'll have a third the acceleration, right? If we halve the mass, we'll have double the acceleration, and so on. So for a set force, the acceleration is dictated by how much mass there is. So that is one way to detect mass, okay? Detect how much mass there is. We call that inertial mass. Inertial mass. The other way is to place the mass in a gravitational field, because gravity pulls on matter, okay? So if we have a nice big, planet, and it has a gravitational field around it, and we take our mass, and we put it near the surface, okay, we can actually like put this on a scale that is calibrated to measure kilograms, and what we're really doing here is we're measuring how hard, how powerfully gravity is pulling on that amount of matter. If we double the amount of mass, so we double the m, we'll get twice the amount of kilograms, okay, as long as we're sticking with the same matter, right? Does that make sense? Kind of, hopefully? Okay, so really what it's coming back to, what we're dancing around here, is it's kind of like a consequence or a relationship of this. So mass is here, force is here, acceleration is here. If we keep this set, we raise mass up, acceleration must go down. Higher mass, lower acceleration. Lower mass, higher acceleration. We're not all that interested at this point in inertial mass. It's kind of a way to sort of wrap your head around what mass is. If I take this rock to the middle of space and I start pushing and pulling it, okay, it will behave the same as it does when it's in a gravity field. In other words, if I, push it with, X amount of newtons, it would accelerate the same way as it would in a gravitational field. I don't know if I'm saying that right, but the idea is this: the mass has not changed between here and here. It's the same whether we're dealing with it outside of a gravitational field or whether we're dealing with it in a gravitational field. So we're going to focus on this scenario, okay? So we bring a mass around to the surface of Earth and we start to measure it, okay? So what we're going to talk about now is this concept of weight. Weight, okay? Weight is equal to mg. So what do we mean by that? Well, what we mean is that weight is the force of gravity which is exerted on a mass by Earth's gravitational field. Okay? So weight is mg. You will often see weight also written just as Fg. Okay? In other words, it's a force. So weight is the force that G causes on mass. So we can do a little problem with that in mind. So for example, find the weight of a 10 kg mass on Earth. Okay. All right, so here's Earth. We know that G is this. Okay. Here it is. Here's my 10 kilograms. And we know that weight is going to be equal to m times g. So my mass was 10 kilograms, negative 9.81. Which way does this point, by the way? Which way does weight point? Yeah, weight is down. Okay. So you get 98. And what units would we be in here? Kilograms times an acceleration should be a kilogram meters per second squared is called a, it's the unit of force, a Newton. So weight is measured in newtons. So when you get on a scale that tells you the number of kilograms that you weigh, quote unquote weigh, actually what that's telling you is your mass. Okay? To find your weight, you have to take your mass and you have to multiply it by the field strength. Okay? Your mass would be the same wherever you went in space, whereas your weight would differ depending what G you're in. So for example, let's say you took this 10 kilogram mass to the surface of the moon. The moon's like all like cratery and stuff. So it's all like this. Okay, so you go to the surface of the moon, you take that 10 kg mass there, and it turns out G for the moon, the G value for the moon is actually 1.6 meters per second squared. Okay, so your weight on the moon, we'll call it W on the moon, is equal to m times G, which is 10 kgs. That does not change, times 1.6 meters per second squared. And on the moon, this 10 kg is 16 newtons.